Well, thank you very much, and thank you for the opportunity to present the work of our team. Um, I entitled the talk Hydrology and Climate, the State of the Science and Future Challenges. And of course, the work I'm presenting is not just coming from myself, but is the result of the work by many people. So I wanted to start with this picture, which you all recognize is the picture of our blue marble, taken from the Apollo 16 as well. And the main characteristic of our planet is precisely that, the blue color, right? You can see it by this hydrosphere that is in continuous cycling, the presence of the oceans, the clouds, rivers like the Nile. And essentially, that cycling of water is bringing life to different ecosystems on Earth. And it's bringing life because we don't know of any form of life that requires no water. And in fact, when we look for life out of space, we look for water. So there is plenty of water in our planet, but for some reason, actually, there is also water scarcity. And if we look for the word climate in Google today, one of the main figures or main pictures that you get is actually this one that you see on the screen, which indicates that there is some form of societal concern about our future tilting it in a direction that is not just warmer, but potentially drier and more hostile to ecosystems, right? So in the past few years, we have experienced actually droughts and heat waves and floods that some of us consider as a window into the future. Because if we look at our model predictions for the future, these events are pretty much globally going to exacerbate. So as scientists, we need to understand a bit better whether this picture is a real societal concern and is based on evidence. And I think that that comes with a series of challenges, some of them which I'm going to elaborate on in the next slides. So first of all, I think we need to acknowledge that the water cycle as we studied it in high school has changed quite a lot. And now it's not just the sun providing energy for water to evaporate and so on, but we have created a very thick blanket of greenhouse gases that also passes on a lot of energy to the land surface that contributes to evaporating water. So we can safely assume that the emission of CO2, for instance, has increased the amount of evaporation that occurs and the amount of water vapor that is in the atmosphere. Now, the water vapor in the atmosphere will eventually precipitate, lead to rainfall, potentially runoff, and groundwater recharge, and so on. So this is the general picture of the hydrological cycle. We have kind of like extended the size of the engine that powers this hydrological cycle by emitting greenhouse gases, right? So conventional hydrology focuses on this part of the hydrological cycle that goes from rainfall to runoff. So essentially, we have a bunch of hydrological models that convert the amount of water that we get from the clouds into recharge, into runoff in our rivers, and so on. But the part that we have to focus on if we want to understand better the impact of climate change on hydrology is, in fact, this other part of the hydrological cycle, which goes from soil moisture all the way to precipitation. So how is soil moisture changing? How is evaporation changing as a function of the forcing that we essentially exert into our atmosphere by emitting greenhouse gases and aerosols and so on? How is that water in the atmosphere reacting and turning into rainfall? To what degree is it doing it more or less than it did before? And only understanding this part of the hydrological cycle will be able to predict better water availability over the continents as we move into the future. And there are two sides of the problem here. It's not just about understanding better how hydrology is changing as a function of climate change, but also how the changes in hydrology, such as changes in soil moisture, but also changes in vegetation, are in turn affecting temperature and precipitation occurrence. So it's not just about the impact of climate on hydrology, but also about the feedback of hydrology on climate. And to understand both and how they interact, as I said before, we are still facing a series of challenges. And the main challenge, or one of the most important ones at this stage, is how to bring humans into the picture. because there are plenty of human activities such as agriculture, industry, that we are not representing properly in our land surface models and in our climate models. We have very poor representation of, for instance, irrigation and so on, households. So all that would need to be actually better reflected in our models to be able to predict in an accurate manner the fate of our water availability. So it's not just about changes in climate, whether they are anthropogenic or they are natural, but it's also what do we do with water once it reaches the land that will determine the availability for societies, right? So this is something that we are doing very poorly at incorporating in our climate models, and which relates, in fact, to this point in the Horizon Europe program that I listed in here. So this is a first challenge, but there are others. One very important, which is actually one of our core research fields in my group, is how hydrology influences climate extremes. So what do I mean by that? Well, we have heat waves, we have droughts, we have floods that are actually modulated by a series of land feedbacks on the atmosphere. So essentially, you can think of, for instance, the picture that you have here. If we are moving into a future that is warmer because of, for instance, CO2 emission, then when the summer comes, it's likely that the soil will be already drier. And if it is drier and we have an anticyclonic condition with little rainfall and maybe also high temperatures, it's likely that that will turn into a heat wave or a drought. Why? Because there is not much water in the system to evaporate. And evaporation is a bit of a buffer for these climatic extremes. So if you don't have water in the system to evaporate, what will occur is that the atmosphere will dry out and will warm up faster. And as it dries out and it warms up, then you'll have a higher chances of experiencing a heat wave or a drought in that particular location. So we understand now that the very severe events that have occurred in the last few years, they actually were quite related to an exacerbation of these feedbacks. So this influence of a land surface hydrology on climate and climate extremes is still not very well understood, and is certainly not well understood at the larger scales. So not just the influence locally, but if you actually put wind in the equation and think that all the interaction between the land and the atmosphere is not just affecting droughts and heat waves at the local scale, but that air can actually flow into a downwind location and advect into that location, then you can understand that it's not just a means for self-intensifying drought and heat wave events, but potentially also a means for self-propagating in time and space these events. So you can see as a unit these heat waves, droughts, but also floods moving in time and space, essentially allowing its own movement via the occurrence of these land atmospheric feedbacks. So they essentially self-propagate. Do we understand these processes? Not well enough. And at the current stage, actually, we need to understand them better to be able to predict these events better, not just in the future, but also for short-term forecasting of these events, so that we have time to adapt to the occurrence and the impacts of these events. And of course, this also gives us a possibility to mitigate and adapt the occurrence of these events in other ways via, for instance, geoengineering solutions. So if you plant a forest, will that have an influence on the occurrence of meteorological drought and heat waves and floods in the region? And will it actually have an influence downwind, maybe thousands of kilometers away? So those kind of questions, they are still not very well understood in the interaction between hydrology and climate. Another question that is certainly not well understood is how plants are behaving, how they are changing, how they are influencing hydrology, but also how they are changing climate. And this is something that we are also investing quite a lot of energy in my group to understand better. What I'm showing you here is just an animation of the Amazon rainforest, and the purpose of it is to show you that this forest, just by consuming thousands and thousands of liters of water per day, is actually pumping a lot of water into the atmosphere, because all the water that is being absorbed by the roots, pretty much the totality is actually evaporated, transpired into the atmosphere. That causes a lot of water vapor and cloud formation over the Amazon, but also going downwind all the way to Africa, potentially causing rainfall there. So we need to understand these interactions between soil, vegetation, and atmosphere that are bidirectional. So it's not just climate affecting ecosystems, but also ecosystems affecting climate. And we need to understand the local effects, but also the teleconnected effects of these interactions. And this relates, of course, to the availability of in situ data of forestry variables, for instance, to understand a bit better these physics and how these processes occur. And that links to this particular point in the Horizon Europe program. And then is a deeper question of plant physiology when we actually look at, for instance, what is the influence of CO2 into the vegetation. So if we actually think of long-term climate change, it's not just about whether forests will have, for instance, sufficient precipitation to grow and an adequate temperature, but also how they will react to the availability of CO2. We know that CO2 per se is actually not bad for plants. In fact, it's their food, so plants are not particularly unhappy when we emit CO2 into the atmosphere. But we need to understand the degree to which they are going to grow due to the emission of CO2, or whether they are just going to become more efficient at using water. Because the difference between the two will picture a very different future for us. In one of them, maybe we have more vegetation, maybe we have more water availability. In a different, and if plants actually change their behavior, we may actually have a completely different future in which we have less rainfall and potentially lower growth of our ecosystems. And these interactions are not just about hydrology and vegetation, but also have important implications for instance, temperature in different regions of the world, as I'm showing in this article here that we published a couple of years ago. So to keep in mind that even microscale behaviors of plant cells in relation to their use of water and their photosynthesis and so on have an implication that can be at the large scale global and even lead to teleconnected interactions at the planetary scale. So those things, they need to be actually better modeled, and they need to be also essentially understood from the observations that we currently have, which are very frequently not sufficient. And then finally, I wanted to tackle that point, the point of insufficient data. Now, in hydrology, but also in climate science, we have to embrace this future data that we are receiving, because it's not just about the in situ measurements, which are of course crucial. And I put here put in this point of the program, the Horizon Europe program that deals with acquiring in situ observation data sets, which is absolutely crucial, but also to the remote sensing data, which is experiencing in the last 2 decades a very severe revolution, because we essentially started privatizing space, and now we have more satellites in space that are managed by private companies than by space agencies. So that's how much the picture is changing. And that comes with a bunch of new data that has a higher spatial and temporal resolution, and that allows us to model and to observe processes that we weren't able to observe before. And now the question is, how do we ingest all that information into our models? And at the same time, also, how can we actually squeeze the information that is in these observations to understand our physics better? And that is something that we are all busy with. In my team in particular, we are actually trying to squeeze information from the Sentinel constellation, but also from other data sets. We built a model that is a model of evaporation and root zone soil moisture to understand a bit better the impact of climate on hydrology, but also potential feedbacks of hydrology on climate is this GLEAM model. So we are now trying to apply to higher resolutions with new data from satellite observations, so that we can also use this data for better agricultural practice planning, water management, and so on. So with that, I leave you. I hope I have given you a rather comprehensive picture of some of the challenges that we are facing in this interaction between hydrology and climate. And I thank you very much for your attention and welcome any question.